Okay, so the last speaker for this morning is Jonas Peters, which is an associate professor in statistics at the University of Copenhagen, and is a member of the Junge Akademie. So sorry for the accent. Even in English it's bad, or in Danish it's, or in German, I don't know, it's even worse. So previously, Jonas has been leading the causality group at the MPI for Intelligent System in Tübingen, and was a Marie Curie fellow at the Seminar for Statistics at the ETH in Zurich. He studied mathematics in Heidelberg, sorry, and Cambridge. And so it's difficult word for me. And he did his PhD with, again, sorry for the accent, with Professor Schölkopf, Janzing and Bühlmann. And his thesis received the ETH medal. And finally, he has been working with Bottou and at Microsoft Research, with Marie Curie at Berkeley, and with Spirtes at Carnegie Mellon. And this morning he's going to speak about connection between causality and machine learning.
Thanks a lot. So can you hear me? Okay. Thanks a lot for the introduction and also for the invitation. It's really a pleasure to be here. This talk is going to be a bit of an experiment. So I will talk about different ideas, and usually I'm not a big fan of this, but I thought maybe this could trigger some discussion in the afternoon. So let's see. The problem, however, is that I have to skip a lot of details, and so therefore whenever something is unclear, which may happen, please at any time just interrupt and ask. It's definitely because of the presentation, I guess. So, I mean, I'm going to talk about several ideas, and this is really joint work with a lot of different people. So I also have the references in the slides, so you will see them again later. I will start with something that I now really started to like, because this is, I mean, if you take this slide home from this talk, I'm more than happy. So let's consider the following problem. So this is really what is causality about. I will want to talk about the connections between causality and machine learning, and first we have to understand what is causality. So consider the following problem here. So we have the activity, let's say the expression level of a gene A, and we have some phenotype, doesn't matter what it is, and you have some data, and you see that clearly there's a correlation. So maybe you see the same picture if you look at a different gene B, and again we have some correlation, and here it's even the same correlation coefficient. So what we are very good at nowadays is sort of to predict. For example, if you now, let's say we observe that the expression level of gene B lies somewhere around 2, then we can predict what happens to the phenotype. So what's the best prediction for the phenotype? So this is a prediction that we have done like 1 million times in our life, and that we are pretty good at. Now, the following question is slightly more difficult. So now let's say, let's try to predict what happens to the phenotype if we delete this gene A. So it's really, I'm not a biologist, but it's really possible to delete this gene, so it's not, I mean, there's no way that this gene is expressed anymore, and so let's say the expression goes down to 0. So then the question is, what is the best prediction for this phenotype? So this is not observational anymore, because we really actively deleted this gene, and now we're asking, well, what's the best prediction here for the phenotype? And you can ask the same question for this gene B. So now, what's the whole point of this slide? Is that causality matters. And why is this? So imagine that the causal structure of the problem looks like this. So let's say that the gene A is really causing, it's a causal factor for the phenotype. So then what it means is that if you're deleting this gene A, so we put a hammer and like change the value of gene A so that the expression level goes down to 0, then the best thing we can predict for the phenotype is something around, that it lies somewhere around here. So this is the linear model, if you like. And this linear model still holds if this is our causal structure. But now, what happens if you have a different underlying causal structure, something like this? So let's say there's even another gene that we sometimes call confounder that is causing both the phenotype and the gene B. So this can still lead to such a dependency, because whenever gene B is, say, large, so it's largely expressed, this means that this other hidden gene is also expressed, and this means maybe that the phenotype is large. But now what happens if we intervene? So if we put a hammer and sort of destroy this gene B, well, what happens to the phenotype? Nothing. It does what it always does. And this means the best thing we can predict is that it says, we say, okay, it lies somewhere around this, this usual range. So that's the sort of the whole point. So the statement is that if you want to answer such kind of question, you have to include causal knowledge. And if you think that causality is something, I don't know, magical or mystical, or you don't like it, that's fine. But so then you have to sort of deal with the fact that you're never ever going to answer this kind of question. So this is like here, if you want to answer this interventional question, that's what we call it, you really have to know the causal structure. Any question about this? Okay, very good. And here, this is like, this is becoming important for the talk. So here we would say that gene A is a causal predictor, and here we would say that gene B is a non-causal predictor. So I will be a bit sloppy on the definitions because of time. Something else that you realize is that this model here, this is invariant. So now what we are going to say is that this is sort of one environment. So you can also think of distribution. So this is one distribution. But now if you intervene, so if you put a hammer and destroy something in your system, we have seen about non-stationarity assumptions. So here we see data from a different distribution, or you may also call it a different environment. And so here in the first case, you see that the model how to predict the phenotype from the gene A, this is the same in both worlds. It's the same in this world and in this world. So this is why we call it an invariant model. Whereas here it's not true anymore. So here we have a dependence between gene B and the phenotype. And then in the second distribution, or in the second world, whatever you want to call it, it's a different model. So this is a non-invariant model. So this will become important later. Good. So you can ask, so why do we want to do this? If you're interested in what happens if you delete the gene, just do it in practice. So just perform the intervention and then looks what happens. And in many systems, we are doing this. In the medical sector, we are doing randomized experiments, which is exactly this. But in many other situations, it's much more difficult to intervene. And one example that I want to show you, is something that I experienced yesterday. So this is a cartoon with a conductor, and it says like wave hands around till music stops. So what's the idea behind this comic? It's to say that the conductor doesn't have a causal influence on the quality of music, so he stands in front of the orchestra and the musicians do what they always do, so there's no causal link. This is a system, so if you want to draw it causally, it maybe looks a bit like this. So you have the quality of the sound, simplified, of course. You have the quality of the orchestra and the quality of the conductor. And then the question is, well, what is this causal link? And this cartoon suggests there's no causal link. So now, if you want to analyze this, you have to intervene in the system. So what do? You just replace the conductor. Because the rationale would be to say that, well, good orchestras tend to have good conductors. So, good orchestras tend to have good conductors. So if you have a good conductor, of course, the sound is good, but this is only because it's a good orchestra. So what you would need to do is you have to replace the conductor with some amateur. This, however, doesn't happen because all these people paying a lot of money for going to the concerts. But yesterday I went to the Philharmonie in Paris, and this is one of the most famous conductors, and he was sick. So this is a brilliant way of intervening in the system, because what they did is they replaced the conductor with a pianist. So this is Pletnev, a very good pianist, but he's not he doesn't have an education as a conductor. But so they replaced him, and then you can see the effect. But this is only, of course, one data point. The second data point is they also, actually, when he played the piano part, they also put one of the violinists as like in front of the orchestra to conduct. And as you can see here, it's really like a violinist. It's not a conductor. And then you can see the effect, right? So this is how you intervene. So you keep everything the same. So the orchestra prepared everything. You don't change the orchestra. You're just intervening. You're replacing one part, and in this case, the conductor. And believe me, there is a causal effect who is conducting and what the quality of the sound is. But this is like only two data points, and this is what you have a lot in practice. I mean, you can do these interventional experiments. Sometimes they are like very time-consuming. Sometimes they're very expensive, and sometimes, of course, they're not feasible because of ethical reasons in the medical sector, for example. So this is what drives me to the to the first question. So when we can't intervene, so this is a very rare case, even for orchestras. So what can you do then? And this is sort of this is the first idea I would like to talk about. So I would like to analyze: can we somehow find these causal models even if we cannot intervene on the system? And so here I put causal in parentheses because what you have seen before is that there's a very close connection to this invariance. So these causal models, they tend to be the invariant models. And maybe, even if you're not interested in the causal models, you should be interested in the invariant models. Because these are the things that you can use even if a lot of things change in your real system. Okay, so let's do this. So this is, again, I'm skipping a lot of definitions here, but hopefully the intuition is clear. So now what we are going to do is we are looking at some random variable y. This is our target variable, and we would like to find the causal predictors. And so this is the causal structure that is unknown. And let's just say that we have data from this system, and this is just the pairs plot. So here we have 3 possible predictors and 1 target variable, and you see that there's a lot of correlation in the data. So let's say we are given data from this world, and then we are also given data from a second world that we may call a second environment, where we are sort of looking at the same system, but now it's in a different state. So you can think of this being a plant inside, this being a plant outside. Maybe this is like under some drought conditions or whatever you like. So now the system changes, but you don't know how it changes. So it's still the same variables. We are still interested in y, but now sort of we are given the data in what we call a second environment. And the question is, can we somehow combine these 2 data sets and try find the causal predictors? And in this case, this is x3. So this is our target. So just as a sort of sanity check, what would you do? What would happen if you pool the data? So now we just combine the data, and I mean you still get a data set that is of double size, of course. And now if you want to infer the parents of y from the pool data, what could you do? I mean, the first thing maybe you would do is you run a regression. And this is the output of R. Of course, you can use any other language as well. So what you're doing is, this is like, this vector contains the 3 predictors. You're just fitting a linear model from y on x. And then you look at the results. And here what you see is that all these predictors are highly significant. So there's no difference between the causal and the non-causal predictors. All of them are very good predictors. So this is what we don't want. So something that we were working on is a method that I very briefly describe in a second, where you basically do something that is a bit more fancy than a linear model. And I will show you the output. So what you do is, we call this invariant causal prediction. So you do not only plug in the x's and the y's, but you also say in which environment you are. And this is just a sequence of 1s and 2s. So there's nothing else. You don't have to specify what the environment is, so in which way it differs from the first environment. You just have to say that it is different. So these are all 1s and these are all 2s. And then, so you run the method that we call ICP. And what you get out is that these 3 variables now differ. So they are all good predictors, as we have seen in the slide before, but not all of them are causal. And here you see that the method correctly picks out the 3rd variable. This is the causal variable. And this knowledge you may use later. Okay, so maybe one way, so one slide about what is this ICP doing, and I'm trying to concentrate on the main idea here. So what we are assuming, this is now phrased in a linear fashion. This can be extended without problems. So what is the setup? So here we have our target variable y, and we are looking for the parents of y. We are looking for the causes of y. This is what we are interested in. And so now the assumption that we have is that we have an invariant model over all environments. So what is an environment? An environment, we put an index small e here, and the calligraphic E is the set of all environments. So what is the main assumption? The main assumption is that we don't care what the distribution of x is, but this is the crucial part here. We say that there exists a model that holds in all different environments. So in all different environments E, we have that y is a function of x, it's a linear function of x, and it's always the same linear function of x, so we are always using the same gamma star, plus some noise, and the noise has a distribution that is also the same in all environments. So this is the assumption. So we're saying there exists a subset S star such that we have the same invariance in all environments. Does this make sense? Or any questions about this? So this is the underlying assumption, and this suffices. This is enough. So we don't need anything else. So then, so this is just notation. So in this case, we would say that this set S star, these are the causal predictors that we are looking for. They satisfy invariant prediction, or you can also, I mean, if you want to do statistics, it's beneficial to phrase this as a hypothesis to say, well, the null hypothesis of invariant prediction is correct, and this really depends now on the set of environments. So this is the underlying assumption, and then what do we do in practice now? So even if we know that this holds, what do? We have these two different data sets, think of the slide before, and now we want to say, well, how do we find S star? So this is really the goal. Find S star, we are given data from different environments. So what do? This is maybe not surprising. So we go, I mean, in practice you do something a bit more efficient, but in principle you want to go through, you take a candidate set S, and you go through all these possible candidate sets S, and then you always check whether this invariant prediction is satisfied or not. And for the true set, it will be satisfied. But for many other sets, it will also be satisfied. And then what you do, it's not super important for the rest of the talk, but you take the intersection. That's sort of the main trick. So you take the intersection of all these good candidates that satisfy this null hypothesis. And why I mean, you don't have to care for the details, but why do I say this? Because it very easily follows now, it's the last comment about this method, you get a very nice guarantee for this method. And it looks as follows. The math is trivial, but I think the result is pretty neat. So you get, by this procedure, you get out an estimated set of causal predictors. This we call S hat of E. And now the statement is that the goal is to find S star. And sometimes you don't find S star. But the statement is that you always find a subset. So with a very large probability, 1 minus alpha, the output of your method is a subset of the true causal predictors. And this is quite neat, I think, because in some situations, maybe your method will not output anything, but if it does, you're pretty certain that it's correct. And the code that you have seen before, so there we saw like that the variable 3 was significant, and because of this result, you know that, well then with a very large probability, it's really, I mean, it's one of the true causal predictors. Okay, and this is like, this is something that you may use, especially if you have like, it's a bit funny because what happens now is that this identifiability comes from the difference in environments. So often we are trying to get our data very clean and reproducible, and we are like looking for, we are sort of, I mean, unsatisfied if the ID assumption is violated, but in this sense it's good. Because the difference in environments, so exactly this non-stationarity, this helps you to find sort of the causal predictors here. This is really where the identifiability of causality comes into play. And even if you don't care about causality, so I would argue that this is still an interesting model because it's invariant. So you find models that hold in exactly the same way over all environments. Any questions about this? I know that this is super dense, so I think what you have to remember is sort of this part. So we are trying to find the causal parents, and there is a procedure, it doesn't matter exactly how it works, that outputs something that is, with a large probability, a subset of the true causal parents. Yes?
In principle, there's nothing that precludes it using a nonlinear relation, right?
No.
It's just the complexity. So in principle, there's nothing.
Yeah,
It's good. So in principle, there is nothing that precludes you from using nonlinear relation. In fact, you can use any type of structured relation.
Exactly. So you can even, I mean, you can argue, I mean, if you like deep learning, just put a deep neural net in here. It doesn't matter. I mean, this just has to be, you have to be able, in practice, you have to be able to test this null hypothesis. So you have to be able to check whether this invariant prediction is satisfied or not. And this you can do with many other models. Nonlinear models is not a problem. Yeah.
And as a follow-up, so how do you deal with, I mean, you could have in principle lots and lots of false positives, right? I mean, do you advocate to something like FDR or some other discovery rate control?
You don't have to. So there's the magic, no?
Yeah, but the magic, this only gives you the intersection property, right? You might want. I mean,
so if you're asking about power, this is a different issue. Okay,
power.
Sorry.
That's a question.
Okay, yeah. So the question is, what is the power of this method? So maybe 2 comments on this. I mean, something it's not shown here analytically. This will depend. So you can analyze this. We have tried our best to do so. So the power depends on the environments. Because imagine this. So you can even apply this method when the biologist told you, aha, I have 3 different environments, but in fact they're all the same. So then you don't have any power. So then the output will be empty. It has to be, because the identifiability comes from the environments. So what you can analyze now is how different have the environments to be in order to get an equality sign here. And this you can analyze, at least in the population setting, it's not very difficult. So in this sense, it's a very good question, and we are starting to address this, but I mean, especially with finite samples, it's not so easy, so if anyone is willing to help, we are more than happy to receive that help. A second question maybe, in causality, so a lot of people will answer this differently, but my point of view is the following. In causal discovery, you want to find causes, but I don't believe in this thing that you're analyzing a genetic network with 4,000 genes, and then you get the correct causal graph, whatever this is supposed to be. I believe, or I hope, that these causal discovery methods will guide the practitioners. So in gene regulatory networks, you have 4,000 possible intervention targets. Not like in the orchestra where you just have one, you just replace the conductor. And then the hope is that these methods will guide the practitioners to say, look at these 5 genes. They are the most promising ones. And in this case, you don't, I mean, this thing, the coverage guarantee is more important in terms of than power. That's maybe the second answer to the question, but very good point. Yeah.
Thank you.
Okay, I mean, because of timing, maybe I skip this. So we did this maybe very briefly. So what is the real data that we looked at? It's gene data where you have expression level of a lot of genes in yeast, and you're trying to find causal genes. And what is nice about this data set is that you have interventions. So let's say these are 2 different genes here with 2 different numbers, as you see, and you have some correlation between the expression levels. And now what is nice is that the practitioners, so they have some interventional data, meaning for some genes they actually deleted the gene, the expression level goes down, as you can see here, and then the expression level of this gene also goes down at the same time, and this means that this gene must be a causal effect of this gene, because whenever you're intervening on this guy changes as well. So maybe it's not a direct effect, but there must be a causal effect. So this is nice about this data, because you have access to some ground truth. And this you can exploit to test your methods. So maybe so details here don't matter. But so that you get an expression where is the field at the moment. So here what you see is some sort of ROC type curve. So here you have so these methods always predict, okay, gene number 12 is a cause of gene number 27, and then you can look in the data whether this is real the truth or not. So, and this is what you see here. So this is the number of sort of intervention predictions. So maybe the first one the method is most certain about, and then you check whether it's correct or not. And if it's correct, you go up 1 step. So the identity is the best thing you can reach. So then you try the second one, and again, if it's correct, you go up 1 step. And so this is the best thing that you can do. And sort of the gray area here, this is a 99% prediction interval for random guessing, if you like. And this is really, I mean, I'm not saying it solves causality whatsoever, but I really do think that it's promising, because what you see here is that because of this built-in coverage guarantee, you really see that most of the predictions that you're making, at least at the beginning, are correct. And this is like highly different from random guessing. So these two curves here, these are two variations of this method, one including hidden variables. So this is sort of a real data set where we do see, I think, some evidence that these causal ideas transfer to practice as well. Good. This is also always all what I wanted to say about this first idea. So how do we find causal predictors in practice, and how can we exploit dirty data in order to do so? This is fine? Good. So then I will like to talk again. This is really like, I don't know whether you want to call this appetizer or maybe not, but so this is just showing some ideas where connections between causality and machine learning could play a role. This is something that is also a proof of concept, if you like. There are many open questions about this, so it's also only showing one possible direction. It's about systematic noise removal, and this is motivated, this joint work with the people in Tübingen and also with the lab in New York. So the motivation comes from an applied problem. So this is a satellite. It's a Kepler satellite that looks into part of the sky. So here you might, I don't know, it's the swan. We call it swan in German. I don't know, this Cygnus or whatever it's called. This, maybe you recognize this the shape of stars here. And this is the field that Kepler looks at. It looks at very different, a high number of stars. And what the goal is of the satellite is to find exoplanets. So that's sort of where the motivation comes from. Here's another picture. This is the Milky Way. This is the position of our sun. And this is sort of the field of view of this telescope. So it's pretty impressive, I think. 3,000 light years. So what is the idea? The idea is to find exoplanets. And how do you do this? There are a couple of methods. And so this Kepler telescope does it in the following way. So you observe a star. And you observe the light curve of the star over time. That's the light intensity, if you like. And whenever you have a planet orbiting this star, then the intensity goes down a bit. And now what if this planet is orbiting and you observe for a long time, this dip will occur like in a periodic manner. So yeah, like if you have an orbit of 1 month, then every month you see this dip. The problem, however, as you can imagine, because I mean, if you're measuring a star that is 3,000 light years away, so that the data doesn't look like this, but it looks like this. And so the question is, how can we find these dips? And now this is an example of a method that I would say is motivated from a causal point of view, but I wouldn't claim that it's brand new, but I think it's something that, if you think about the causal structure of this problem, that is very easy to find and to come up with. Okay, so how does the causal structure look like? So you have something that is unobserved. This is what you're interested in. This is the true signal. This is the true light curve, the true light intensity of the star. And you are only measuring it. So you're measuring it with this Kepler satellite. And the problem is now that you have some systematic noise. And there are different sources of this noise. So one is that sort of the satellite is moving, so it's actually broken, I think. So it always drifts a bit. And so in this sense, it's a systematic noise, because at the same time, you're not only measuring one star, but you're measuring thousands of stars. And this drift, for example, this affects all of the measurements of all these thousands of stars at the same time. So this is somewhat one source of systematic noise that you have. And of course, you have the display and so on. And so the point is now that this systematic noise also affects a lot of other measurements from other stars. And now the question is, how can we sort of use the measurements of other stars in order to find a good estimate for our true signal? And now this is a causal assumption that is, if you like, trivial. But the point is, so here imagine being a lot of other stars as well. And the point is now, if you're measuring stars that are thousands of light years away from each other, there's very little reason to believe that they should be affecting each other. So basically, you're plugging in the assumption that the light curves, the true light curves that you don't have because you only have measurements of these very far distant stars are independent of each other. And this you're exploiting. So if you're familiar with the Markov condition, you can also read this off. So imagine here being another star that influences the other measurements, and then you're just saying the true signal of this star that you are observing and of all the other stars that you're observing at the same time. These are just independent. You can read off from the graph. Okay, how do you exploit this? So this is if you like, a very straightforward ad hoc method. But what we are now assuming, this is important, is that the measurement, this y, this is affected by the true signal. This is the true star, and this is the satellite. This is the systematic noise, and you assume that they are affected in an additive way. I mean, you can of course reparameterize here, and then what do? This is the, sort of the most, and if you like, trivial idea here. So you remove from y, you remove everything that can be explained by x. Because now imagine that this y and x, so these are signals over time, and that they share some common properties. And if you see this, you should be suspicious, because you're saying, well, these are totally different stars. So whenever they share some properties, it must come from the systematic noise. There's no other way. And this is what you're this is the main rationale. So you're saying, okay, whenever I can explain something from I using x, then I can remove it because it must be due to this systematic noise. So in a way, it's a trivial idea. And mathematically, you need this assumption of additivity in order to prove that you're really doing better afterwards. However, so I think this idea is we haven't thought about this a lot, but I would be interested in asking, well, how far can you go here? Because this idea seems to be more general than just looking at additive structures. Anyhow, if you believe that additivity is what you do, what you have, then what you do in order to reconstruct, so this is our goal, right? So we want to reconstruct the true signal, so let's write down an estimate that we call Q hat. And what we are doing is we are taking the measurement y and we are subtracting everything that we can explain by x. So a trivial method, if you like. And then, I mean, this is, I don't know, doing some mathematics. It's not surprising, but it tells you that you're not totally off, if you like. So whenever you can perfectly reconstruct f of n, so whenever there's a function of x such that this is the same as f of n, then you get a perfect reconstruction of the correct signal q. Another thing is that if you have less and less noise, so here you're saying that x basically recovers the full information about the systematic noise, then you can also get perfect reconstruction of q in the limit of the low noise. Also not surprising. This is a bit more relevant, I think, in our scenario. So the third option that you have is if you observe many versions of this x, and this is really true in this satellite data, because there you have thousands of stars, and you always you have many measurements of stars, and this you can also show quite easily that in this regime you are also able to reconstruct this q. Okay, I think the idea hopefully came across. So how does it look on this data set? So this is the real data that you have, and this is a very clear point. So here you see the drift, I think. So the light intensity goes down. Here you have these gaps. This is always when the satellite turns back to Earth and sends the signal. And here you see the dips. So here's one, here's one, here's one, here's one, here's one, here's one. So this is the measurement, and then this is when we apply our sort of systematic noise removal. So here you see that the signal to noise ratio is much better, right? So here it's much easier to find these dips than in this data. And this is sort of state of the art, what people have done before. So it's a bit better. It's not a revolution, but I think it's nice to see that these causal ideas in such a simple method is actually competitive. So this is another example where you have a bit more noise. So, and here you can imagine that in this picture now it's even harder to see this dip, right? But here it's becoming a bit easier. So here you see the blue lines. This is the periodic time whenever the planet is orbiting and occluding parts of the star. Okay, I mean you can, so it's really, apparently it's better than state of the art. I don't go into details here, but they even found, so some of the exoplanets were confirmed now. So they found, I didn't do the experiments, this was done in New York, but they found they had new candidates for exoplanets, and apparently they're confirmed now, which is nice. It's not making money, I guess, but still nice to see. Good. Any questions about this idea? Good. So how much time do I have? 12 minutes. Okay, so maybe I'll do one more idea and then skip the last one. So this is something that I would also like to talk a bit about reinforcement learning, and this is really, I mean, it's a start. So this is not a fully developed methodology in any sense, but this is really an attempt to connect these two fields, reinforcement learning and causality. So what I see until now is that in some scenarios you are using causal ideas to improve methods, and you could have done so otherwise as well, but it's sort of the causal point of view helps you to develop these methods. They are quite natural if you come from this causality point of view. But I'm not saying that you can strictly beat other methods, as you will see, but maybe it's an attempt to enforce this connection. Good. So what we looked at, this is an example. This is blackjack. Hopefully you know the rules very quickly. Maybe so you play against the bank. And here, what happens is that you get two cards. So let's look at this person here. So he has a 10 and a 4, so it's 14. And then you can always decide whether you draw a card or whether you stand. And you want to get as close as possible to 21. But you don't want to what is called bust, I think. So you don't want to go over 21. And then so you play. You always say draw another card or stand. And then at some point you stop. And then the bank starts to play according to a deterministic strategy. And then you see whether you have more points than the dealer. And if so, you get the money. And otherwise, you lose the money. So let's see what happened here. So this person, for example, he has a king and a jack. This is 20 points. So apparently this is a good card. It's a good hand, so he stands. Then the dealer, he started with an ace, and then he draw a 6, I think. So this is 17. Then according to the deterministic strategy of the dealer, he stops. And then this guy wins. So here you can see the money was doubled. There are a couple of tricky bits. So an ace, for example, can count as a 1 or an 11. So what you see here is like he starts with 13 points, he draws another card, it's a king. So then you would think it's bust because it's like 23, but it's not, because then you can count the ace as a 1. So he has 13, draws another card, it's 16, but then he loses against 17. So here you see no money. That's sort of in a nutshell what blackjack is about. What I found nice about this game is that you know the optimal strategy. So this is known from a math paper. You can look it up if you don't count cards. Otherwise, it's a bit more difficult. Good, and this you can play with. You can now, I mean, you have seen the reinforcement learning framework before, so I would now frame this as a causality framework, but you will realize that it's almost the same, but it draws attention maybe to slightly different things. So what is the data that we are given? So now the idea is you go into a bank and you have a system, into casino, you have a system and you play randomly, you play some games according to a strategy and you want to find the optimal strategy. So what is the data that you have? So this is a sample from this distribution, so X, Y, Z, you see an example later, so you get some data from this distribution, and for every game, so some of the X and Y's may be observed, so maybe it's your hand, the other one, the Y is the dealer, the hand from the dealer, some of the things are hidden, because maybe it's the deck of cards or whatever, and then you receive some rewards, so this is money on whether you win or lose money, and this depends now of course, on these variables x, y, z. So now, what is finding a good strategy? So I would say it's an intervention. So you have your joint distribution, and now it's an intervention. I didn't define it properly, but it's something like this. So you take one of these conditionals in your distribution, and you replace it by something else. So if you think about the example before, we have this gene B, if you remember the right-hand side, this gene B depended on the confounder, and now we deleted this gene. So we are putting a hammer, and we are now saying, no, this gene, the expression level of gene B shouldn't depend on anything else anymore, but we set it to 0. So if you like, mathematically, what you're doing is you're taking one of these conditionals and replacing it by something else. I mean, this is very dense, but so this is very similar to what you're doing here. You have a certain strategy, So for example, how y depends on x. And now changing the strategy is an intervention because you're taking this conditional and you replace it by something else. But so you only change this part, the rest of the distribution stays the same. So this is in a nutshell what an intervention is. So here it's really the strategy is the decisions you make given the game state. So as an example, so what are the values of xi, yi and so on? Let's look at this blackjack example. So xi may be your hand. It's king of hearts, 9 of hearts. And then yi is the decision whether you hit or stand. And the zi is something that you don't know, maybe the game state of the deck, for example. And then all what you do is you observe, of course, I mean, you know what you have played. You have played yi according to your random strategy, whatever. And then you realize whether you have lost the money or here, because this is called a blackjack, you even win 1.5 times your money. So here, this is sort of the data that you're looking at, and now the question is, what is the best strategy? So from a causal point of view, you would formulate it like this. So given that we are allowed to intervene, so we are allowed to use any strategy that we like, so this P star, what is sort of the expectation of our loss given this P star? And then, of course, you want to ask, well, what is the optimal P star? So under which P star does this thing become as large as possible? Does this make sense? It's a bit of an experiment. I know that sort of it's slightly confusing when you see these causal point of views for the first time. Is there anyone able to express a question? Okay. Mm-hmm. So this is sort of the framework that we are trying to do, and really think of a strategy as this conditional. So given that I have the data, so given that I see the open cards, what is the best decision that I can make? Can I hit or stand? Okay, so now what is the mathematics behind it? And funnily enough, this we have seen a couple of times in different forms today. Because again, this is a variation of reinforcement learning, if you like, of importance sampling, if you like. So this is the thing that we're interested in. And we are interested in underplaying the strategy P star. What is the expected loss? So what do you write down? Well, it's just an integral. It's an expectation, right? So you integrate L with respect to this P star. And now, so the first step is trivial. So the first step is just dividing and multiplying by P, and then the second step, this is sort of the key point of importance sampling, and this we have seen before. So what you're now doing is, what you're saying is, the only way in which P star and P change is the strategy. I'm not changing the rules of the game. I'm not changing the distribution of cards. I'm only changing the strategy, meaning I'm only changing the way I make decisions given I see cards. And this is why this factor simplifies a lot according to this. Okay, it's a bit of mathematics, but what it shows you is that it's very easy to estimate these things. If you keep track of this, I mean, in the first talk it was the probabilities. Here it's almost the same thing. So if you keep track of these weights, then it's very easy to estimate this guy, because I mean, this is now the data. You have data from P, so you play with a certain strategy, and then you're wondering, well, how well would I be if I play a different strategy? And then you can just take your samples, take your data points, and reweight them according to these weights here. Okay, and I'm almost there now, because in practice what you realize is that these weights behave very badly. We have seen this. This is a question of variance. This estimator is often, if you have big data sets and heavy tails, so this is often dominated by a few weights that are enormously large. And like all the rest, the 99% of your data doesn't contribute, because you have very few weights that are extremely large. Okay, and there are two. You can also compute confidence intervals. But I want to conclude with sort of two ideas how to make these WIs better behave. I skip this. So this is the first one. This is about, I call this state simplification. This is about blackjack, and this is really a trivial observation, if you like. So you have the deck, and the deck determines some hidden cards and some open cards, and you base your decision on the open cards. And now what you see, and this is trivial, it may include some prior knowledge. Maybe you don't know the rules of the game, but maybe someone at some point you realize, well, the fact whether you lose money or not only depends on the doesn't depend on the suit of the card. It only depends on whether it's a king or not. It doesn't matter whether it's spades or clubs. And this you can exploit, because if you know, this is a causal assumption if you like, if you know that the lost money doesn't depend on the cards, but only on the cards without suit, then what you can do is you can also base your decision on this. And mathematically you can show this leads to a much better behaving weights at the end. A second idea, in advertisement, this is something that we did with Leon Bottou. It's the same, sort of a very similar idea. So this is a super simplified version of advertisement placement. You have some user intention that hopefully is unknown. You have some user data, as we have seen before, search query, whatsoever. You have something that they call the mainline reserve, or they used to call it. So it's a parameter that determines if you search something on Google, how many ads do you show above the search results. This is always between 0 and 4. And this is a parameter that you can set, and then at some point the user clicks or not. And again, so what you want to do is you have this click, and maybe you want to optimize this, of course under constraints. But this is sort of the strategy that you can play with. So this is like a mainline reserve. Again, same story. You gather data from your strategy, you do a lot of biddings, and then you're asking, well, how well would I have been doing if I have chosen a different strategy? And again, you have these problems with high weights. What's the trick here? The trick here is that you know that the user never sees the mainline reserve. It only sees the number of ads in the mainline. So what this means is that you can exploit the fact that this is a discrete number. It's 0, 1, 2, 3, or 4, whereas this is a real parameter. And if you do the math very, very easy, you get much, much better behaving weights, and you reduce the variance a lot. And this is like due to the, I mean, if you draw this causal graph, it's trivial, because you immediately see, well, the mainline reserve is sort of, I mean, the user never sees it. It just sees the number of ads. So these are the things where can try to exploit the causal structure. We applied this to data. So this is the original confidence intervals. Here's the mainline reserve. If you change it, you try to predict how well would I be doing in terms of clicks. And here you see the confidence intervals. If you include this method, you see that the confidence intervals reduce significantly. And this is just exploiting a trivial causal statement, if you like. Good. That's all what I want. Well, that's almost all what I wanted to say. But I come to the conclusion. So I showed sort of 3 out of these 4 ideas. The first one was discovery of causal predictors, and I tried to argue that these invariant models are of interest in itself. So you get causal predictors, but they're not only causal, they also lead to invariant models. I showed you this, what we sometimes call half-sibling regression. This was the exoplanet idea, where we try to remove systematic noise. And I very briefly talked about an attempt to connect reinforcement learning with causal structure. And so this is really, I mean, it's ongoing work, and it's not finalized, and I think it's an interesting field of research. With this, thanks a lot.
So we might have time for a very quick question that anybody has. Sorry.
Okay, I have a quick question on part 1, and I was a bit confused about the idea of environment. You know,
can you repeat?
Environment.
Mm-hmm.
Because if you have IID data, you can still see it as coming from 2 environments. Assume that one of the features is binary, for instance. Then you have 2 environments from your IID data. So could you tell us more about how can I use your method? It seems that I can use it even if I have a single environment, just by thresholding a random one of the feature.
Yeah, so maybe 2 comments on this. So we don't have to specify what an environment is. So that's, I think, what's one of the beauties of the method. Methods, of course, I'm biased there, but you don't have to specify. So if someone has an IID data set and splits it in half into environments randomly, then the coverage would still hold. So you would just get out nothing, because it really exploits the difference in the environments. So now what you suggested is to say, well, just take one of the variables and threshold. So you're constructing environments arbitrarily. And there you have to be a bit careful. So this is totally fine as long as you're not using an effect variable for doing this. So if you have some prior knowledge and know, and this often happens, I think, you happen to know that one variable is certainly a causal, what we call ancestor of the target variable, then you are happy to do so. And this is also what we are exploiting at the moment. There's something, I don't know whether you're familiar with these ideas, but there's something called an instrumental variable that they use a lot in causal discovery, especially in economics. And this is, so you can show that this is a general version of instrumental variables, if you like. And there it's the same idea. You are using, you're constructing one anchor, one variable that you know it's certainly coming before causally, like it's an ancestor of the target variable. And then you can do so. This is something that we are trying to exploit at the moment. So how to construct environments, because especially, of course it's a buzzword, but if you have big data, so if you have a lot of data, this is something interesting to look at, no? So can you reconstruct environments that give you sensible output in terms of causal discovery? Very good point.